Thank you everyone for being here. Thank you everyone for settling down for our last morning session. It's going to be very exciting because we have our academic researchers here. Academic research is so important to us at New York State DOT and many other agencies and bodies and the private sector, the public sector, because that's what we base many of our decisions on. As Joe Terrier mentioned earlier, all the bios are in this wonderful program that you have in your hands. And therefore, I'm going to omit the details on our wonderful presenters this morning. And we're going to, but you can read up on them in your flyer. We're going to start our session with Dr. Angela Sanguinetti. And she is a board-certified behavior analyst and environmental psychologist from the University of California. She's going to talk to us about a behavioral review of eco-driving. So please welcome Dr. Angela.
Thank you, Elizabeth, and thanks to everyone. Thanks for the invitation, Penny, to come speak today. I'm very excited to share with you all my perspective as a behavioral scientist on the current state of academic research on eco-driving. Oh, I'm not forwarding it. That's fine. So one of my first assignments as a postdoc at the Institute of Transportation Studies at UC Davis was to review the literature on eco-driving and to assess the degree to which it could be enhanced by integrating strong behavioral theory and research methods. So today I'm going to present some of my key findings from that review and some research that has emerged from it. And to begin my review, I asked the simple basic question, what is eco-driving? As a behavior analyst, my first step in approaching any topic is to define the target behaviors. Because how you define your target behaviors has a lot of implications for what you're going to do to try to change those behaviors to come up with the best strategies and interventions. And also, good operational definition is critical for consistent measurement and verification of behavioral interventions. So I reviewed the literature looking for a definition that met some criteria for a good behavioral definition of eco-driving, things like comprehensiveness. So I wanted to find a definition that told me every behavior that's eco-driving and just a well-bounded, clear definition with all the behaviors. And again, so if we know all the behaviors, that's going to enable the best estimates of the savings impact in terms of fuel economy and GHG emissions. We have to know all the behaviors so we can get a good estimate of what the potential impact could be, and that's, of course, important for from a policy perspective. I was also looking for consistency and precision. So are we all in agreement about the behaviors that we're calling eco-driving? What exactly are they? So again, in order to develop really effective interventions, it's probably good to know exactly what you're encouraging drivers to do. And finally, what may seem like a duh factor, I wanted to make sure that we're actually defining behavior. And more on that in a minute. But as it turned out, the existing literature on eco-driving really didn't satisfy these criteria. To begin with, I couldn't find anywhere a comprehensive list of eco-driving behaviors. Just couldn't find it. So, for example, some people typically limit their discussion of eco-driving to operational driving behaviors, so mainly your driver's interaction with pedals and the steering wheel, whereas others have a more inclusive definition that includes maintenance practices, equipment purchases, even your choice of vehicle. And even when sources agree about a particular behavior that they all say is eco-driving, they define it differently and describe it differently. For example, I found different sources that variously recommended eco-driving to be accelerating gently, moderately, or even quickly. So, which is it? We need a little more precision. And then finally, a lot of definitions of eco-driving describe what a driver should not do. So don't idle, don't speed, don't drive aggressively. Whereas a more effective approach, a behavioral approach, is to promote replacement behaviors for those anti-eco-driving behaviors, if you will. For example, turn off the engine is a target behavior rather than don't idle. A famous slogan among behaviorists is, if a dead man can do it, it ain't behavior. So that just stresses the importance of targeting actual positive actions in a behavioral intervention. So bottom line, from a behavioral science perspective, I just wasn't satisfied with existing definitions of eco-driving. So we worked on developing a definition that was more comprehensive and more precise. The first thing we did is we created a boundary for this phenomenon of eco-driving, and we said that we were going to use so we define eco-driving as exactly those behaviors that are kind of assumed away and excluded from the CAFE standards fuel economy estimates posted on every new car. And those behaviors, of course, are reflected in the caveat on the Monroney sticker. Actual results will vary for many reasons, including how you drive and maintain your vehicle. So that's eco-driving. So this definition of eco-driving excludes things like mode share and vehicle choice, but it basically includes everything you do with a given vehicle once you have it. That is eco-driving. So now we had some boundaries for a definition of eco-driving. We synthesized and analyzed descriptions of eco-driving behaviors from both academic research and popular media. And we came up with 6 categories of eco-driving behavior. We broke driving behavior down into 5 subcategories: accelerating, cruising, decelerating, waiting, and parking. So this research is done. We have a whole paper on the analysis, and if you'd like to see that, I'd love to share, so you can contact me. So this typology and more nuanced definition of eco-driving is valuable for a few reasons. So first of all, it provides us with a framework to start thinking about how to target different types of eco-driving behavior, not a one-size-fits-all approach, but can we target all these things, and what interventions are best suited to which behaviors? And it also just better reflects the extent of opportunities to improve fuel economy and reduce GHG emissions through driver behavior. For example, we think that the Monroney sticker could actually more accurately read, actual results will vary for many reasons, including how you drive and maintain your vehicle, and how you manage cabin comfort, plan your trips, manage vehicle loads, and fuel your vehicle. So we can make it a little more eloquent than that, perhaps, but you get the picture. So now that we had this behavioral definition, satisfactory behavioral definition, I reviewed the research considering the potential impact of eco-driving in terms of both fuel economy improvements and reduced GHG emissions. As a framework for understanding these impacts, I use this equation suggested by environmental psychologist Paul Stern to determine the impact of any action that could potentially mitigate climate change. And the equation states that the overall impact of the action, I, is a function of the technical potential for savings, T, which is the savings achieved by the behavior, and behavioral plasticity, P, which is the proportion of drivers or people that you can get to adopt the behavior out of the total population, N. And applying this equation to eco-driving, we added the term K to reflect the multitude of different eco-driving behaviors, which we've just established, each with a different technical potential and behavioral plasticity. And therefore, the total impact of eco-driving would be the sum of the impact of all of the impacts of all of the eco-driving behaviors. So this is just a behavioral framework that's really useful when you're considering estimates of the impact of eco-driving, whether they're your own estimates or someone else's that you're trying to interpret. For example, a lot of estimates of eco-driving impact focus on technical potential only. Technical potential is relatively easy to determine because you can take the driver out of the equation and you can figure out the impact of each eco-driving behavior through lab experiments, simulations, and modeling. Some really interesting research on technical potential was done by Civic and Shuttle, published in Transport Policy. They offered estimates for the technical potential of a wide variety of different eco-driving behaviors, including those that we refer to in our new typology as driving, maintenance, load management, and cabin comfort behaviors. And they frame impacts as the potential for decrease in fuel economy if you neglect all eco-driving behavior. So if you're doing everything wrong. And they summed the impact of all these anti-eco-driving behaviors to be a potential of a 45% decrease in fuel economy. So assuming a baseline of anti-eco-driving, so things like driving for 20% of the time at 90 miles per hour, the technical potential of eco-driving could theoretically be 45% improvement in fuel economy if you start out doing everything wrong. So of course that's not realistic for most drivers, thank goodness. The author's goal wasn't to determine average technical potential, but more like maximum technical potential. But this is just an application of this framework. So in addition to technical potential, the actual impact of eco-driving is also dependent upon behavioral plasticity, the degree to which drivers will adopt the behavior. And to understand behavioral plasticity, we really need real-world studies or field studies of drivers and their actual behaviors. For example, in one study, participants in an eco-driving program reduced idling, but they didn't change their acceleration or speed behaviors. Unfortunately, though, lots of real-world studies don't measure actual behavior. They tend to just measure fuel economy. In rare cases, they do, but we still don't know a lot about the behavioral plasticity of different eco-driving behaviors. Hopefully, large, extensive data sets like we're getting with DASH now, we could maybe start to look at behavioral plasticities of different behaviors and sticking an OBD in every car when you're running an eco-driving program. So now that we understood the target behaviors and how to evaluate the impact of eco-driving, the next step was to start to consider interventions to promote eco-driving, how to best promote it. And I focused on in-vehicle feedback. That's really the most common type of eco-driving intervention in the academic research in terms of field studies, real-world studies. And fuel savings and emissions reductions outcomes in those feedback studies are a measure of impact, so they're a function of both technical potential and behavioral plasticity. And to date, we found 27 academic peer-reviewed studies of in-vehicle feedback interventions for eco-driving, and the impacts average out to about 6% increase in fuel economy for this strategy. And the behaviors that are usually being targeted are driving behaviors, and in particular, acceleration, cruising, decelerating. And although the average impact in these studies is 6% reduction in fuel consumption, the effects range really widely, from negative impacts to over 18% fuel savings. And some of this variation is probably due to different target behaviors, different behavioral plasticities, but it's also probably due to the extremely wide variation in the types of feedback being provided to drivers. So each study in the academic peer-reviewed research typically develops its own feedback system that's unique, and most studies just compare one type of feedback to nothing rather than comparing multiple types of feedback. So the research has clearly shown multiple times that something is typically better than nothing, which is great. It's the best first step, but now we've established that, it's time to start thinking about what are the features of feedback that contribute to more or less effective interventions, which types of feedback are more effective for which eco-driving behaviors, and in what contexts. So along these lines, we've developed a typology of in-vehicle feedback to begin to investigate more systematically what makes feedback more or less effective. And for this typology, we analyzed in-vehicle systems developed by vehicle manufacturers, so systems that are commercially available on the market in cars you could buy, mainly in plug-in hybrid and electric vehicles, because that's where they're proliferating, even though they could be applicable to gas-only vehicles. And we analyzed, we found 15 types of feedback that are distinct in terms of behaviorally relevant features, such as, are they targeting specific behaviors? If so, which? Immediacy of the feedback with respect to the target behaviors. Is it immediate? Is it delayed? All kinds of, we have about 12 to 15 features that we coded all these feedback systems on. And this research is also completed. So again, if you're interested, please contact me. I'd love to share it. Here you see some images that represent a few of the types of feedback we identified. And our next project that we're hoping to complete is a meta-analysis of existing eco-driving feedback studies. So a meta-analysis is a statistical method of combining findings from many studies. And this would give us actually the best estimate to date of the impact of feedback on eco-driving. And it could also reveal aspects of feedback that affect the impact, such as the target behaviors and immediacy and other things like that. It could also reveal aspects of the programs or interventions themselves that are leading to better or worse impacts. So for example, duration of a study. Lots of these feedback studies are like 2 weeks long, 3 weeks long, but energy feedback in different contexts, like residential energy feedback, there's hundreds of studies on that. Energy feedback is kind of notorious for having a novelty effect, where it's pretty effective for a few weeks and then kind of wears off and people go back to their established former behaviors. Which is one reason why I really like the auditory feedback. It's much harder to ignore. If anyone ever tries to not buckle their seatbelt, then you're familiar with auditory feedback that can control your behavior. That beeping can be quite annoying. So some takeaways, whether you're developing eco-driving programs, evaluating them, or just considering them, you can take a behavioral science perspective by defining the target behaviors, measuring the target behaviors as well as driver attitudes before, during, and after an intervention, whenever possible, and comparing different treatments rather than something to nothing. So if you can do any of these things, it will really help to further our collective knowledge about eco-driving. So that's a behavioral perspective on eco-driving, and I'd like to acknowledge our funders and our PI on the research, principal investigator, Dr. Ken Karani, also at UC Davis with me. So thanks very much.
Thank you, Dr. Angela. That was very interesting. And we will hold the questions until after the speakers are done. So, because they're all talking about eco-driving and similar topics. So we will do that. While you're doing your job, I will introduce Dr. Kanok Bori Bun Samzin. Did I get that right?
Yes.
All right. Well, thank you so much for allowing me to pronounce your name. Dr. Kanok is a research engineer with the UC at Riverside, and he's going to talk to us about evaluating real-world impacts of eco-driving. Please welcome Dr. Kanok.
Thank you, Angela, for the introduction. And also thank you, the conference organizing committee and conference sponsor, for having me here today. Angela set the stage nicely for my presentation, where I will looking at evaluating real-world impacts of eco-driving. Just to clarify, my presentation focused on what Angela called the technical potential of eco-driving intervention and how we can evaluate it in real world. So as Angela mentioned, many studies have been conducted to look at this technical potential of basically fuel-saving potential of eco-driving. And why is it important? Because drivers, fleet managers, and policymakers need to know these numbers to make informed decisions about whether to adopt eco-driving or to implement any eco-driving intervention, right? And for all the studies that have been conducted to date, there are many approaches in terms of setting. It can be done in something like a control environment, such as driving simulator, or across driving cars that has no other traffic interacting with the driver. But really, what is the most important evaluation is probably the real-world evaluation. Policymakers definitely interested in the real-world potential of this technology. Often, the eco-driving studies often use before and after study design because of low cost, it's convenient and simple. But a lot of the time, the study did not address the temporal changes during the before and after study period. So in a way, it's not as simple as we think, and we will look into why. First of all, your mileage may vary. Real-world fuel economy can be affected by a lot of factors. Obviously, the first one is driving behavior, which is something that eco-driving try to intervene and influence. But real-world MPG can also be affected by a lot more factors like extra weight, carry, tire pressure, and road grade, for example. All the factors in blue, these kind of impact vehicle fuel consumption rate, how much fuel you need to burn in order to move the car per unit time or per unit distance. For example, if during the before period you drive alone, and then during the after period you kind of carpool with another person or more than 2 persons, you have extra weight and your real world fuel economy will go down. Aside from the factors in blue, the factors in green can also influence how your vehicles operate. For example, during one period, you just kind of go commute to work and back home, but then during the after study, you take a road trip and drive mostly on freeway, so your fuel economy will go up, but because of not because of your driving behavior, but because of your travel pattern change. So in this talk, we're gonna try to see how we can account for these temporal changes during the before and after period of data collection. So I'm gonna use one example system. Back in 2011, our research center started a 3-year research program funded by DOE to develop a driving feedback system. And one of the technology that came out of that project is the eco driving feedback system that is shown on the slide. It provides real-time feedback to the drivers, and there are many types of feedback. For example, eco speed band, which based on real-time traffic information suggests to the driver what speed you should be driving at. And it also provides several warnings, aggressive acceleration or braking, or excessive idling in both visual and also audio context, and other things too. The system also serves as the data collection tool, just like Dash, where it taps into OBD readers, OBD part of the vehicle, and able to read vehicle and engine information, including fuel consumption of the vehicle. And the data were collected on a second-by-second basis, so we have a rich set of data as well. So this slide, I introduced a metric called vehicle-specific power. It looks busy, but basically what it is the metric that estimates how much energy or how much power is needed to move the vehicle at a certain speed and acceleration to overcome a lot of resistant force, for example, aerodynamic drag from the wind, or for the vehicle to climb hill. So in real world, all those factors will change, right, every second. And it may not be the same during the before and after study period. But if we control every other variables in this equation to be a constant and only vary the speed and acceleration which are driven by driving behavior, then what we can do is we can calculate a VSP values and then correlate that with fuel consumption on a second-by-second basis. And then we can create this plot, which is what I call normalized fuel consumption rate. What you see in the error bar is basically all the noise coming from the different headwind that you experience, the different weight that you may carry in the real world from both study period. But with the regression to a mean, if I take the mean values for each of the VSP values to represent the average or normalized fuel consumption rate of how I drive for a combination of speed and acceleration, then we basically normalize a lot of factors that were not controlled in real world. Now, the next set of slides, we'll look at how we can adjust our data to take care of the differences in vehicle operating patterns between the before and after period. And basically, it can be done by adjusting for specific driving behaviors that influenced by the driving feedback system. In the example that I use, the warning provide to the driver when they accelerate too aggressively, brake too aggressively, and idle for too long. So we will just look at these 3 specific behaviors. But the framework can be applied to other behaviors such as speeding as well. And the concept is to analyze the impact of each of these driving behavior as if the vehicle was subject to the same operating pattern. If during the both study period, the vehicle were driven equally on freeway and city street, were carrying the same amount of load and things like that. So let's look at the specific detail. First of all, we define what we call driving scenarios, and there are 16 of them splitting by 2 road types, highway, cities, and also 8 speed groups. And then based on this definition, we analyze the data and look at how our eco-driving feedback system influence the acceleration and braking behavior. The blue lines in each of the plots show the baseline behavior, and the red lines show the behavior with the feedback system. Take one example. When we analyze the data of acceleration in the city, we can see that with the feedback, the acceleration become milder on average across all the speed, the driving speed domain. It's true also on highway. In the same way, deceleration on city street and highway also become milder. And these are desirable behaviors that we expect of eco-driving feedback system. Now, when we look at the fuel consumption rate using the normalized fuel consumption rate that we calculate earlier, then we can calculate what is the typical fuel consumption rate under each of the 16 scenarios. And because of the milder acceleration and braking, we will see that most of the time, for most of the scenarios, the average fuel consumption rate with the feedback system become lower. And that makes sense, right? And the bottom plots is what I call vehicle operating patterns earlier. How much time you spend driving under each of the 16 scenarios. So in the city, you would expect a lot of low speed driving because you get stuck at traffic light. So there's a lot of idling time here. On the other hand, on highway, you're cruising at highway speed, so you have more time spent at higher speed. And this distribution of time are constructed using the driving data from both periods. So basically, we assume that if the driver were subject to this type of operating pattern in both periods, what would be their fuel consumption? And you would expect fuel consumption during the feedback to be lower because for each driving scenario, the average fuel consumption rate is lower. Now, after we adjust for acceleration and braking, now we're gonna try to adjust for idling. And for idling, we cannot just penalize every idling, right? Sometimes you stuck at traffic light and that's unavoidable. But excessive idling is not desirable for sure because you waste fuel and create emissions. So what we define what we call unnecessary idling rate, which is the total idling time beyond a certain threshold. It could be 5 minutes or it could be 10 minutes, subject to local regulation or something. And that amount of time per hour of vehicle operating time. And for this particular example, we have, if we look at the top left bottom, we see that during the baseline period, the vehicle has a lot of idling event. Maybe the vehicle was driven mostly on city street and then they have to stop at traffic light for very often. But that idling period is pretty brief, about 1 minute. But if you look at just the unnecessary idling rate, which is in this case defined as 5 minutes or longer, we will see that the feedback encourage driver to reduce the amount of unnecessary idling. So the rate become lower, whether we use the threshold of 5 minutes or 10 minutes. I'm sorry to have to throw up a set of equations, but I think it's necessary to understand how these are adjusted. So the first equation basically calculates how much time, how much fuel was actually consumed in real world due to excessive idling. The second equation calculates how much fuel would have been consumed if the unnecessary idling rate was applied to the data. And then the last equation basically take out the actual fuel consumption and then add back the hypothetical fuel consumption because of the unnecessary idling rate. Let's look at the results. And for this particular vehicle, oh, and by the way, this is a shuttle bus, so don't surprise when you see the fuel economy to be 7 miles per gallon. This is a shuttle bus that kind of pick up and drop off passenger in a paratransit fashion. So it has a lot of idling time, and fuel economy is typically lower than normal truck. And based on quite a bit amount of data that we collect. So if we look at the fuel economy that was collected from the vehicle during the baseline and feedback, we see that the improvement was only 2.4%. But with appropriate adjustment that was done, then the adjusted fuel economy actually showed that the change is 4.2%. So that's a big difference, right? I took subway here, so I didn't know what is the gas price today in New York. $2 per gallon? Okay, 210, sure. So for $2 a gallon, 2% may not be a big deal for a driver, but 4% may, it's kind of almost double the benefit, right? And it still seems low for some drivers, but at some point, if Dallas ASLAB onto the emission that come off the tailpipe, 4% might be a significant change that could incentivize the driver to change their driving behavior. So in conclusion, real-world evaluation of eco-driving needs to account for factors that affect vehicle fuel economy beyond just their driving behavior. I time myself out, so that's worked perfectly.
Thank you.
Oh, can I mention the last slide? I just want to acknowledge the U.S. Department of Energy for sponsoring the study and all of the project partners. Thank you.
Thank you. Now, before we move on to our third and last speaker of the session, I wanted to mention that Penny told me earlier that lunch got moved to this building, so we kind of gained back a little bit of time because we don't have to walk to 61st Street. So we will go a little bit over here because we don't have to leave the building for our lunch. That's why we don't have to worry about time right now. And when you're ready, it's my honor to now introduce Dr. Ray Zimmerman. She is a professor of planning and public administration right here in New York City at the NYU Wagner Graduate School of Public Service. And today, she is going to speak to us about issues of intermodal connectivity and eco-mobility. Please welcome Dr. Zimmerman.
Okay, thank you, Elizabeth. Yeah. Okay. This morning, if it's still the morning, I am going to be addressing eco-mobility, not eco-driving so much, even though I'm looking at the interface. I'll be looking at the following things, some of which you are already very familiar with. What are we talking about when we're talking about modes? Secondarily, what have been the trends in those modes? And then really the drivers, energy use and energy intensity, and then greenhouse gas emissions per unit of driving. And then the heart of it is the interconnectivity. Does that help? And I do want to focus on a lot of the research funded by UTRC that we have produced on, zooming in on the bus-subway connectivity, which can be expanded to other modes. Okay. How do you? I'm moving it this way. Maybe it's this way. These keys don't, oh, maybe this one works. There we go. It's the bottom using, okay. So first of all, the modes that, what are we talking about? Most of us, well, do I press the sender? Okay, okay. And back is, okay. Okay, so the modes that we're talking about, we all know that it's driving alone that really dominates here, at least in the last few decades. And this, again, many of you are familiar with. This is the road transportation usage compared with capacity and some of the drivers. And what the upper left shows is that vehicle miles of travel to a large extent is tracking motor fuel usage. To the right, it's tracking population growth. And the bottom, the roadway capacity, is not really tracking at all the vehicle miles of travel. To some extent, lane miles are increasing because we're increasing width, not necessarily length. And this is the same. And here, shifting over to public transportation, the obvious dominance of bus rapid transit, heavy rail, our subways and so forth, and commuter rail account for a large part of the passenger miles and passenger trips. We zoom down into the cities, comparing. This comes out of, no surprise, New York City's work on inventory of greenhouse gas emissions, percentage of commuters using sustainable transportation. The U.S. average is the dark green, New York City over there, and that really reflects transit matters. Biking, going up and up, but still only accounting for a small proportion of trips, as does walking, a larger proportion than biking, still going up. And this is bike share as opposed to personal biking, just a smattering of various cities, just ones that I happen to be in, Washington, D.C., New York before it got launched, Chattanooga, and Bordeaux, France. It's just, anywhere that I've been. Now, zeroing in on energy use, the issue here is that transportation accounts for 72% of petroleum usage. Back a few years ago, it's been increasing up and up, and looking at the bottom, not using much renewable, 13% of renewable energy consumption is accounted for by transportation. However, the flip side, only 4% of energy used in the transportation sector is from renewable. Energy use comparatively all over the world. This is a 2005 and 1990 comparison. Transport is actually increasing in the amount of energy use. This is from an interesting paper by Shreya Dev from MIT showing energy usage by mode. Again, the auto travel the most. And out of Oak Ridge National Lab, we see that even within rail, energy intensity, switching from use to intensity, is actually highly variable from city to city, whether it's light rail, commuter rail, or heavy rail. This is what I want to focus on here, that both energy use by mode and energy intensity by mode shows the dominance of road-based vehicles, personal trucks, cars using the most, Here, buses, transit, because they're using energy as well, demand response, trucks and cars really dominating the picture. So now switching from energy to greenhouse gas emissions, 70% of greenhouse gas emissions due to urban transport choices. This is out of the Rosenzweig et al. Work that they've just come out with all over the world. And the 90% of the growth in emissions is from transport systems in lower income countries. Here again, out of DOT's work, household size affects CO2 emissions and the amount of travel. And this is out of the US EPA annual greenhouse gas emissions. Want to move through this very quickly. Just follow the red arrow. Transportation is really very high in, this is total emissions, CO2 as a proportion of all emissions, and these are the other than CO2 emissions where methane and nitrogen oxide mobile combustion is up on the list there. And again, out of Shreya Dave's work, greenhouse gas emissions pretty much tracks that. And here, this came out of MTA's Greening Mass Transit, again, where the greenhouse gas emissions are highest on the road travel. Transit bus is an exception. Now, not to leave out normal air quality chemicals, just that you should keep in mind that transportation accounts for over half, maybe 2/3 of carbon monoxide and nitrogen oxides as well. Now, what we wanted to look at was intermodal connectivity, and a paper we did, it's been published in Transportation Research Record, but the longer report on which it's based is on the UTRC Region 2 website. What you see here, we've narrowed in on bus connectivity, and heavy rail in New York City, 72%, is this the point? 72% of bus connectivity associated with, of heavy rail connectivity is associated with bus, and quite a lot for intercity. So bus travel is high in New York. It's lower to a large extent in New Jersey. Those were the two areas we were looking at, and the reports detail this. Now, this is out of a study I did on September 11th, 2001, and what attracted me to the multimodal work. In that study, we found that in the initial, the survivors leaving the World Trade Center, collapsing towers, almost all of them used walking, but a number of them used other modes. But then an hour or two or three later, that dropped, and you saw cars and taxis and to some extent rail when it was back up and running. So that shift, this still doesn't capture multiple modes, like when they shifted from one to the next. And this is very important. And even though our survey based on a Columbia University survey didn't capture this is published in Risk Analysis in 2011, we saw that most of the people using 1, 2, 3, 4 modes, most of them used only one within the first hour of escaping. But as you moved out into their ultimate destination, that collapsed. Half of them only used one mode, a quarter 2 modes, 12.7% 3, but at least this begins to capture this multimodal thing. Now, let's look at the physical facilities, and then hoping that people use physical facilities that are nearby. This is just a smattering of rail transit maps all over the country. I have this for the world too. You see a lot of connectivity at high level nodes. This is the New York City map, which is both a spoke system as well as an interconnected matrix with a lot of nodes depending on where you are. And actually, under the street, there's more connectivity, 34th Street, 42nd Street. Now, this is sort of what we want to do in the next stage of our research. Sorry about it, but I colored the green, it's sort of the greener modes, less energy use, less greenhouse gas emissions. Bus transit is the lighter red because it's less, it does use fuel, and the darker green is much greener, intensive, and rail again is more ecologically sound, but there again they also use. Now what we're trying to do is look at the collapse. Okay, what we spent a great deal of time doing is going from this to see to what extent bus transit is near subway, not so much, although we did light rail to some extent in New Jersey. So in that paper and the report that's on this website, we looked at the number of buses stopping within a 10th mile of every single subway station in New York City, and we looked at 3 northeastern New Jersey cities as well. The white little dots are the buses, and the red dots are the subway stations, and the circles represent a 10th mile. We chose that smaller distance because a disabled person would be more amenable to that kind of a distance rather than a half mile or a quarter of a mile. What's interesting is we looked at poorer areas. Do they have as many buses stopping and as many subway stops? And we found if you define poorer as percent below, and this was tract level, although we've now moved to block level data, if you define it as the percent of the population within the tract that is below the poverty line as defined by the federal government, you find definitely a finding. We did a regression analysis, found that in the poorer communities it was much less. And here's 4 of the poorest census tracts in each of the 4 boroughs. And this is median income. This is percent below poverty. This is percent below poverty in Bronx and Brooklyn. These are median incomes, which didn't show as strong findings. However, there were a lot with and without buses nearby, and in fact, very few subway stops. I also looked at terminal points. It turns out, where the subway stations stop. And, there are about 40 of them in the city. And without there's a lot of double counting, but you find that there's a very heavy collection of buses concentrating at the end of the line. There was a wonderful article in the New York Times by Newman that encouraged me to do this work. What happens at the end of the line, and what is the end of the line? It's where there's water, or where there's a park, or where there's other intercity transportation. So at any rate, we did all of this analysis, a lot of connectivity at the end of the line. And it's not only the modes very quickly, but it's how you use them. We're using a lot of land in roads, pavements. US EPA did a very good study of the percentage of pavement used in selected cities, 30 to 50%. And a lot of this, the dark blue over there, is road consumption and road-related parking. So this is a drawing I did that there's a lot of competition on streets and nearby sidewalks for all sorts of modes. And if it looks confusing, it's meant to be confusing. There's a lot of competition. This is something I was in Arizona, and they have a skateboard. This is to store your skateboard. Hadn't seen this in the city, but you know, the competition is coming to a head. This is a walk-only zone on a campus in Arizona. From 8 to 4, you can only walk, no skateboards, no bikes, no nothing. And so what do we do to sort of integrate this? But in other words, it's not only the modes, but integrating the street itself, where you've seen a lot of these trying to separate parking and bikes and so forth, trying to green the sides of roadways with swales, trying to actually green rail lines by eliminating them and substituting them with parks. This is the High Line picture over there, but there are many going on. This is a picture I happened to take in Bordeaux, France, where instead of having asphalt between the rails, you have grass. I hadn't seen it. And then the New York City Transit solar systems. The final thing I want to leave you with is that eco-mobility is responding to disruptions. In other words, it's resilience, reinventing, redistributing buses, for example, for special purposes. These are buses. Anytime there's something, the buses are rerouted and changed in direction. And then we look at sea level rise. These are all the Port Authority facilities that are, the darker the bar, the low, that's towards the 500-year 2090 elevation. So we're in trouble here. This is something our group did. We've mapped every single subway station by floodplain maps and surge zones. And recovery is part of restoration. How fast do you recover? Out of some work that was funded by NSF, 80% came back by November 12th. This is just the transit system in New York City, 80%, which meant that it went all the way through. And then we're very concentrated. The more concentrated we get with our infrastructure, it's going to get kind of hit. Rail as well is highly concentrated. One lightning strike on one computer really hit things pretty badly. And this is, small-scale technological fixes. We're trying to raise the vents over the subways. And we're still trying, this is near my house, still trying to restore our benches on Broadway, but trying to protect and elevate the benches. Okay, and I just want to acknowledge finally the UTRC 2 funded projects, 3 of them, very grateful for the funding, partially supported by NSF funding from an urban resilience and some a rapid grant, and then finally some interdependency work I'm doing with Kwanyan Zhu at NYU Tandon School that helps us look at some connectivity, and then finally all of the colleagues and research scientists. Okay.
Thank you so much.
Sorry for taking so much time.
Thank you.
Okay. Thank you.
So, Dr. Ray, if you would have a seat and we'll take a couple questions. Right, Penny? We have time for a couple of questions? So questions, anyone, for any of the presenters on eco-driving, on interconnectivity here in the city, which really played into the post-Sandy recovery.
Yeah.
Right, we're
very
talking
much
about the
so.
bus bridge. You may have heard about that. So, any questions? Right there.
My question is for Angela. Angela, studying driving behavior and its savings on energy consumption and therefore emissions. Turner Fairbanks Research Building, Federal Highway Administration, is working on the user interface on the speedometer on the dashboard display to help drivers when they approach the next light. Nobody really wants to arrive just as the light is turning red. It's a waste to run up on it, just to wait a minute. Easier just to drive gently and approach it and get there just as it's turning green. Are you familiar with their work, and have you done any studies on such a feedback to help people kind of bunch up and all show up as the light turns green, much as we all show up on a Thursday around 5 p.m. if that's the flight we're boarding.
It's interesting, yeah.
Am I on?
Yes, you
Oh,
are
okay.
on.
I thought I'd turn it on. I'm definitely familiar with the subject, not that particular project. Actually, the way we technically have been